No, I don't have those done yet, but I'll try and get them soon. And the one assignment, those of you that are writing intensive, I need a bibliography and a one-paragraph synopsis of what your written report will be on, or the second written report. That's just for the writing intensive students. So today we're going to talk about carbon NMR. We'll do a little bit of comparison of it to proton NMR in terms of the general facts of carbon versus hydrogen. And then we're going to talk about the chemical shift and all those calculations I kept trying to put in before the last test. We're finally going to get to do some of them. So we're going to do some calculations of chemical shifts using the tables of data rather than just trying to use an approximate correlation table. All right. So this is going to cover 4.1 and 4.2 and Appendix 6 and 7, which is where all the tables of data are. And then essentially we'll be covering the rest of Chapter 4 on Monday, maybe a little bit on Wednesday as well. A lot of it is overlapping material that we've seen before. So let's get started. We talked about proton NMR and how the proton interacts with the magnetic field, and then we get the two different energy states of the carbon nuclei for the spins, and we can compare them using magnetic or the radio frequencies. When we look at the spin quantum numbers, this was from the first part when we were talking about protons, and I truncated that table and just comparing proton and carbon now. The hydrogen 1 has a spin 1/2, and we found from our calculations that 2I plus 1 where I is our nuclear spin quantum number, that there were 2 spin states for hydrogen 1. And that's the main one we focused on when we talk about proton NMR or hydrogen NMR. And the deuterium also had a spin quantum number, but in this case it was 1, so there were actually 3 possible spin states. Carbon 12 has a 0 spin quantum number. Why was it that carbon 12 has a 0 spin quantum number?
Because we have an odd number of things.
Right. Yes, that all studied up for the test. So, proton is an even number. We've got 6 protons. Neutrons, 6 neutrons, so both even numbers. And when you have 2 even numbers for protons and neutrons, they are NMR inactive. They don't have the spin states. Carbon 13, however, has 6 protons, 7 neutrons. And so the odd number of the neutrons gives us a spin quantum number of 1/2. And then we can have a NMR active nuclei where we can see the 2 different spin states. And again, because it's 1/2, we have 2 spin states. Carbon, we know, is weaker than proton. There's a couple reasons for that. The natural abundance, we've talked about this. Carbon 12 is about 98.9%, and carbon 13 is about 1.08% of all the naturally occurring carbons in a molecule, or in any sample. So if you have a naturally occurring sample, then you're going to have probably just 1 carbon that may be carbon 13 in the entire molecule. So we have 10 carbons in the molecule. One of them might be carbon 13, but it's going to be really unlikely that you're going to have more than 1 carbon 13 in the same molecule. And this has a couple consequences. Number one, we need a lot more of the carbons in there in the sample overall in order to get enough sample or enough signal to read. So we need lots of sample. Or if we're doing a Fourier transform NMR, which is the modern use of NMR, you need to take lots of scans so that they can be averaged together so you can get a better signal to noise. So either a lot of sample or a lot of scans in the experiment. The other consequence is that it is very unlikely that you're going to have two carbons right next to each other that are both carbon-13. And so you're not going to see splitting between carbon-13 and carbon-13. The probability of having that would be extremely low. So carbon-13 bonded to a carbon-13 is very unlikely. So we're not going to see splitting. No carbon-carbon splitting. On Monday, we'll talk about proton-carbon splitting, because we know there's lots of protons in the molecule that are NMR active and can cause splitting. And we'll talk about that and how we get rid of it so we can actually see our carbon peaks. But we're not going to see splitting from carbon-carbon. Occasionally, if someone's trying to study something in the lab, they may synthesize a molecule that actually has a carbon-13 in it. They intentionally put a enriched sample of carbon-13 when they're synthesizing it, and then you can actually see some splitting and some occurrences of that. But for a normal spectra, it's not going to happen. The other problem, or maybe it's not a problem, but just a fact of life for carbon, is that its magnetic gyric ratio for carbon is about a quarter that of the proton. So for proton we had 267.53, and for carbon we had 67.28. So we're about 1/4 of the hydrogen. This has a couple of consequences in all of those equations that we were playing with. When we talk about the molar frequency, or the frequency it takes to excite our proton. So we had this frequency here. This was how much energy it takes, or the type of electromagnetic wave it takes to excite the proton from the lower spin state to the higher spin state. If we keep B0 constant, and 2 pi is always constant for this magnetogyric ratio of hydrogen versus carbon, we're going to see about a quarter reduction in the frequency that we need for the excitation of the carbon from one spin state to the other. If we have a 400 megahertz NMR like we have upstairs, we call it a 400 megahertz, but really this refers to our hydrogen 1 energy that it takes. That's the 400 megahertz of the frequency of light that's required to excite our proton from the lower spin state to the higher spin state. Our carbon is actually going to be 1/4 of that. And so when we use carbon-13 NMR on our instrument, we're actually using 100 megahertz for the radio frequency that we're using on the sample. So it's about 1/4.
Is that why you have to tune the NMR to be like phosphorus or?
That's part of it, yeah. You have to. It's set up automatically to do proton and carbon, but for any other nuclei that has a different magnetic gyric ratio, we would have to tune it to the right frequency so that you can get those transitions. And we're just reviewing all of these concepts from the NMR introduction. Remember, we had this graph that said increasing energy versus your magnetic field. The stronger the magnetic field, the greater energy difference between those. And so for proton, it would look something like this. For the same magnetic fields, we're going to see something that's about a quarter of the difference there. So we're not going to see quite as much of an energy difference between those. And this has a consequence on the population states of the protons in the high spin state versus the low spin state. If you remember, we had that equation that related the number of spins that are in a high spin state versus low spin state, and that related to the energy. So n upper versus n lower is going to be equal to e to the power of delta E over kt. Okay. And if we have a smaller delta E, that means we're going to have fewer of our carbons getting excited into the upper spin state. So not only do we have fewer carbons overall to look at because of the natural abundance, we have fewer going into the upper spin state, which means we're seeing fewer transitions. Both of these cause the carbon to be a lot weaker than the protons. With modern instrumentation, though, it still doesn't take very much. As long as you have enough sample, we're getting really good carbons in lab in about 3 minutes. You can also use very small quantities and run it for a lot longer.
Okay, I just want to make sure.
Yes. Okay.
So even though it takes less energy to excite the carbon-13, you don't see as many transitions?
The energy directly relates to how many are in the upper state versus the lower state. So the lower that energy, the smaller this ratio is going to be.
Okay.
And remember, we were looking at excesses of, when we're looking at 1 million, we're looking at excesses of like 40.
Right.
With certain, we did all those calculations with different field strengths. So if you had only 40 that are exciting and now we have a lower energy, we might only see 10.
Okay.
And so we're only seeing 10 transitions. Now, of course, we're looking at molecules, so you get 6.02 times 10 to the 23rd in a mole. So if you had even a 10,000th of a mole, you have a lot of molecules in there and a lot of atoms, but it still takes a lot of them to see them all. Shauna?
So is delta E the difference between an upper and lower, or is N a different?
Yes, it'd be the difference between these two energy levels. Right.
And what are the units of that? Again, are they going to be like calories or not?
Well, usually we'll use kilojoules for energy, yeah. But for N upper and N lower, when we're talking about the populations here, we're just counting. It was the population of how many protons were in each one, or carbons in this case.
So the last time you gave us this equation, you said that it could also equal E equals the HV over KT.
Yep.
That still applies.
Still applies. Remember that E, delta E is equivalent to H times V, which is our frequency. Yeah.
So how does that play out on the NMR when we look at the carbon NMR and we see it's a weaker signal? I'm having a hard time seeing how that plays out on the carbon NMR.
You probably won't see this too much.
Okay.
It's going to be seen more in the setup of the experiment. And we usually use experiments that are pretty much always set up. You just take a look, go when it runs a carbon. It's set up to run 1,000 scans rather than 16. So you get more signal. The instrument itself is going to change its radio frequency. So it's looking at the 100 megahertz rather than 400.
Because
we don't do that.
Okay, because it knows it's a weaker signal.
Well, the 100 relates to the magnetic gyric ratio, so you have to be able to correlate those. And you do it differently for each atom, or element, I should say.
Okay.
Sorry, it's still negative, right?
Yeah, I think it's fine. Negative sign. Okay, we're not going to go over those calculations. We've done those before. Alternatively, you could do them again, just replacing carbon numbers instead of proton. We're going to do other type of correlations. Any other questions on the differences here? Okay. Overall, it's about 6,000 times weaker for a carbon versus a proton between these two differences. It's a big difference. The carbon NMR chemical shifts are going to look fairly similar in terms of relative positions to the proton chemical shifts. So we had different chemical shifts for our saturated alkanes, which are up there at the top, versus something that's substituted with an electronegative group, versus our sp2 or sp3 hybridized carbons, and then our carbonyls are going to show up. And the same effects apply. So if we're looking at the electronegative atoms here, these are going to be deshielded due to inductive effects. So you have an electronegative chlorine that's going to pull electron density away from the carbon and move it downfield. The one difference between carbon and proton is that the atom that we're looking at, say the bromine, is directly attached to the carbon. So if we have a structure like this, of course we would have other things attached. When we're looking at how the bromine affects the hydrogen, it's 2 bonds away, because you've got the bond to the carbon and then the bond from the carbon to the hydrogen. With carbon NMR, we're looking at a 1 bond difference, and so it's directly attached, so you're going to have a greater electron density withdrawal than you would for the hydrogen. This spreads the entire spectrum out, so instead of going from 0 to 12, we're going from 0 to 240. It's almost 20 times as strong of an effect. So your chemical shift differences are approximately 20 times as great an effect as it would be for the proton. So proton, if we were looking at a carbon bromine or carbon chlorine, we may think that's about 30 to 50. Here we're looking at somewhere between 30 and 80 or 30 and 60. So it's a much stronger effect. And it's going to affect the neighboring carbons more significantly. So if we went 1 more carbon out here, we're just 2 bonds away, which is actually our typical difference for hydrogen. And so it's going to affect it further out along the chain. And we'll see that when we do a few calculations. Your sp2 and sp hybridized carbons have the diamagnetic anisotropy, and that's going to deshield the carbons. And in this case, they're directly involved with the carbon double bond or triple bond. So again, they're more significantly affected by the diamagnetic anisotropy. Your carbonyls have both effects. So we have diamagnetic anisotropy from the double bond. We also have the electronegative inductive effects.
For the triple bond and the double bond, like for the HNMR, wasn't it like deshielded for double bond but shielded for triple bond? And is that different on this one?
It's a little bit different in this one, but you can see it's not as great of an effect for the sp hybridized for the alkyne as it is for the sp2 hybridized alkene. These are numbers you should know. I also put in the carbonyl range, and you should know those numbers or ranges as well, because when you're doing carbon NMR, one thing that shows up here that doesn't show up in our proton are the carbonyl signals, because most of these are not going to have hydrogens attached to them, so you don't see them in the proton NMR. Between this and your IR, you're going to get a lot of information on the type of carbonyl you have, and this is going to help narrow that down.
Can you explain why the bond is at 65 versus double bond? I mean, intuitively, it would seem like it would be stronger effect.
Remember when we were talking about the protons, we went in the opposite direction in terms of the magnetic field? So you had the circulating field here, and that caused a secondary magnetic field, and in this case, if I'm going to draw these correctly, they're aligning with the carbonyl here, whereas with the double bond, we were going against where the hydrogens were. In the end, we drew the little cones that said that this was shielded here, and then out here, it's de-shielded. And here, this area was shielded, and this area is shielded, and then out to the sides was de-shielded. So we actually had the opposite effect where this was shielding the hydrogen here, and this was de-shielding the hydrogen here. The carbon's kind of a little closer to the middle, so it's not quite as shielded here, and this one's still de-shielded. Okay. That's the approximate ranges though, and we want to do some actual calculations to do a more realistic number. There's, say, your aromatic region. It can go from 110 to 160, and you're going to see your carbons throughout that region, but we can actually calculate where they're going to show up on the magnetic spectrum, or the NMR spectrum, based on what is substituted to the benzene, right? Your book in chapter 6 and 7, or appendix 6 and 7, has the full table, or some tables of these numbers. I chopped it down so that I could fit some of it on the slide and still give you an idea. And you're going to want to take that and the equation at the top here and do calculations. So I'll walk you through this first one. I think that's all I'm going to have time for, and then we can do some other examples on Monday. For an aromatic ring, you would use this table for a benzene derivative. We're going to look at methoxy toluene, and this is going to be a paramethoxytoluene. There is ortho, meta, para. Those are our standard substitution patterns that we've seen when we're talking about organic compounds. But when we're talking about carbon, we also care about the substituent, the carbon with the substituent directly attached to it. So we can call that the alpha, or a lot of times it's labeled as the ipso carbon. So the carbon that's directly attached to the substituent is ipso. In the molecule I've drawn here, we have 4 different carbons, and we need to do calculations for each of the carbons in the structure here. So we will start with a base value of 128. If you have benzene by itself, it's going to show up as one signal at 128. So that's our base value for an aromatic ring. When we calculate A, we're going to start with the 128, and then we need to change it based on what is attached at the ipso and paracarbons. I'm going to highlight the two groups we're going to look at. So we're going to look at this methyl and the methoxy here. For carbon A, the methoxy is connected ipso.
How do you pick which one is ipso?
We're just going to look directly at A, so we're looking at carbon A right now,
Oh.
and so it's what's attached to it. So we have an OCH3 group and we have a CH3 group. The OCH3 group is ipso, so we're going to add 33.5 to the base value of 128. And there comes the ring. For carbon A, for carbon A, there is going to be a methyl group that is para. And so we need to add the para value, or in this case, subtract the para value. And I'm just going to label these as para and ipso so we can keep them straight. And when we add that all together, we should get 158.6 parts per million. These are all in parts per million, our chemical shift value. I looked up the actual spectrum. Our actual value is 157.65 parts per million. So we're pretty close.
Does that matter if it's a negative? So
Yeah.
should it be plus the 2.9?
Oh, I'm sorry, there was a correction on this. It's all should be plus para values instead of minus. So correction on your slide. We're summing up all of the substituents here in the equation up at the top.
Dr. Russell,
Mm-hmm.
would you have us memorize this chart?
No, you don't.
I just want to know.
You need some
Tell me
confirmation.
now.
Yeah.
Okay, let's get through one more here. So this was our actual value. You can see it's pretty close to the calculated value. So let's do B now. Here we have our base value of 128. And then we have, if we look at the B, our methoxy is now ortho to carbon B. So we're looking at this one. This is ortho. So now we're going to use the ortho value for our methoxy, which is negative 14.4. And then our methyl group is para, no, not para anymore, because we're right here, so we're going to go with the meta. And the meta, for the methyl, very small correction of negative 0.1 parts per million. And our overall number now is going to be 113.5 parts per million for our calculated value. Our actual value is 113.5 parts per million. All of these numbers come from just taking lots of spectra and averaging them together just like they did on the Woodward-Fisher rules when we did UV vis. So we'll finish that up on Monday. I need to leave you with Dr. Jones. Were there any questions before I leave?